Thank you very much for the kind introduction. Thank you all for joining. Thank you, Godwin, for the invitation. I've been following everything you did in the last year, like for my seminar, and I'm really impressed by everything you organized, and it's a real pleasure to give this talk today to all of you. So today I will give you I entitled it a gentle introduction to machine learning. So the idea is to give you like some basic idea about AI. You know, maybe for you AI is a black box. For many of us, maybe it might be a black box. I try to explain a little bit some concept behind AI. So if you're an AI expert, it might be a little bit boring, but if you don't know too much about AI, maybe you can learn a few concepts around AI and its application to neuroradiology in this talk. So let me quickly move this around. So AI, artificial intelligence, is like the general concept of you know, a computer doing tasks that normally would be required to be done by a human, and machine learning is a sub-concept of this. Machine learning is a part of AI where you basically train a computer to do tasks using data without explicit program. So we differentiate between supervised learning. So that's where you give us ground truth to the computer to learn something. And for example, here you see a stroke, and you're going to give the segmentation to the computer, and you're going to try to train a computer to recognize the stroke. And unsupervised learning. So in unsupervised learning, you're not going to give the source of truth. You're going to let the computer try to find the difference. So if you give a large data set of cases with a stroke and without stroke, and you try to build a network so that the computer understands by itself that there's a difference and tries to separate these two classes. So we didn't differentiate between predictive models. So we try to, for example, classify findings between, for example, stroke, bleeding, and a tumor. Or segmentation is also another example of predictive models, where you try to simply predict the probability that the voxel is going to be a stroke or not a stroke. And then it's somehow like a totally different application of machine learning is generative models, where you try to generate things out of nothing. You know, we're going to see how this can be, how is this possible? Basically, out of noise, you want to train a network to generate an image of a brain, for example. And you could also try to generate new lesions based on modification of image. So we just take a normal image and you're going to train a network to implement a lesion inside this image. You see this stroke implemented inside the normal brain, and we train the network to implement this stroke here. So deep learning, there's been really three factors that led to the recent explosion of deep learning application. The first is just the internet, that the large database of image was accessible all of a sudden. The second is this implementation of convolutional layer. So basically, the idea is that one of this layer inside this network, it looks like this, and what happens is that it extracts if you multiply this image with this convolutional layer, which is just a mathematical operation, it extracts the border of the image, and this made a big difference, mostly because you see that you still recognize the animal in this image. But you see that all the information a lot of very, very important information is in the border of the things you see. And so this convolutional layer made a big difference in the performance of the networks. And the third one that really increased permitted the explosion of machine learning is the development of this graphical card. So basically, these graphical cards permits to make really fast given some operation that was not possible before. So these three concepts, these three things made the whole explosion of machine learning possible. So now I want to go through the main concepts, the main principles behind machine learning. Why does it, how does it actually work? So the first, you really need three things that are really important. The first is a network. And so here you see the representation of a network. So you're going to have different layers and you're going to pass the information between the layers. For example, here it's just going to try to recognize the difference between this dog or this cat. And so you need a network, and you can have different kind of networks, but basically you need a network. The second thing you need is a loss function. And so the loss function, you basically need to define what you want to do with this network. So you need to define a loss function. So for example, one loss function might simply be how many images were classified incorrectly. So you want to have this as low as possible. So this would be one example, but that's not a very good loss function. So we found better, and one is cross entropy loss. That's just a complicated term, but it's not really important. You need different kind of loss functions depending on what kind of performance you want out of your network. And if you define a different network and different loss function, you might do something else with your network. So here's just a simple representation of what it really means. So basically you want the loss function, and you want to minimize this loss function. So for example, you want to minimize the number of images that are classified incorrectly. So you need a way to go there. And so that's the third part that is really important in machine learning, is you need a training strategy. And a training strategy simply means you want to optimize the loss function. So you want to go to the place where you have the smallest loss function. And so again, if you want to classify image, maybe you want to go where the number of misclassified image are the lowest. And so we have again different training strategies, but currently, like really the one that outperforms is gradient descent. But I just put this name here so that you've heard it. Now the neural networks, I just want to explain a little bit like the different parts that are built inside these neural networks. There are really four parts that are really important. One is the feature maps. The second is the convolutional layers. The third is the activation layers. And the fourth is the pool layers. So we're going to go one by one and try to understand what's going on. So basically, a network is simply going to be these feature maps and the operation between them that transform the information from one to the other. So the feature maps are represented usually like this, and this is the first. That's typically what you're going to see. It doesn't depend how many layers you usually have, but the first layer is always going to look like this, and that's a very interesting observation. It reminds me of this. I don't know if you remember, maybe from medical school, this concept that basically in the primary cortex of all primates, you're going to have neurons that's going to get activated basically depending on the orientation of this of the signal. So if you show a cat this kind of image and you move it around, you're going to specific neurons are going to get activated specifically on the orientation of the signal, and so you see it here. So a bar moving in this direction is not going to get any activation, and a bar in this direction is going to get a strong activation for this specific neuron. And you're going to have another neuron that's going to get activated for this information. And when I see these maps, I always think about this because it's kind of interesting to see that this is a fundamental property of these neural networks, is this kind of patterns that actually you also find in the primary visual cortex of all basically all primates. And that's basically, there was a Nobel Prize for David Hubel and Thorsten Wiesel, this finding. So it's a really fundamental finding. Then the deeper you go, the more complex structure you're going to see. So that's why also it's called deep learning, is that you have several depth of your network, and the deeper you go, the more complex you're going to see, more complex structure you're going to see. And so see, this is already like more complex structures in the second layer. And if you go deeper and deeper, you're going to see more and more complex structures. Like here, you start to see image of dogs. So So basically the network is learning. The deeper you go, the deeper the feature maps, the complexity is going to increase, the more complex things the network is going to learn. Yeah, and that's an interesting property of these networks, and that I think it's really interesting to observe this. Yeah, so the second thing is, again, between these feature maps, you basically have these operations, and one is the convolution operation. We discussed this already. So basically, this convolution operation permits to get information of the edge, and to recognize an image. Often the edge is maybe more important than the color of the animal, but maybe the edge helps you more, and that's an important layer that you need to have. Then you have activation layers, and so. And again, if you compare to the biology, so the biology of a neuron is basically a synaptic summation of the information. That's now the equivalent in the neural network. So you also sum the information. So we try to modelize this like this, and that's one part. And the second part is a nonlinear transformation. So again, maybe you remember from medical school. So basically, the neurons, there's only one action potential that's going to flow. It's a yes or no answer. So the neuron is going to sum up all the information to the synapse, and at some point it might shoot an action potential to the axon, and that's what that's what people try to do in neural networks. So you basically need nonlinear transformation. So that's how it looks like. But what's really important here is to understand that they try to sum the information inside the theoretical cell body, and then an output is going to be a yes or no. So that's, for example, here in this max function. So it's going to be a yes or no answer, and this seems to be really important for this all to work. Yeah, so basically it's sum of the information, and this activation, this nonlinear transformation forced to this side. So you really need to take a decision. The third really important part inside between the layers is this pooling layers. So basically what happens here is that you try to reduce the dimension of your feature maps. And why is because, so what happens here is that if you try to learn something, if you reduce the amount of the size of the image, for example, you force the network to learn some concepts rather than just the image. So if you try to learn, for example, what is a dog, and you reduce the information, you force the network to understand the concept behind the dog, and not like just learning that on the upper left part of the image there might be this or this signal. So the UNet, this is the most important network for medical segmentation. This is really what is used, and I even found out there's a very famous paper called NN UNet that showed that whatever you try to do, it's very currently it's not possible to beat the UNet. So they showed that whatever you try to do is changing the structure. The UNet is really the best that you can currently have for medical segmentation. So I want to quickly go through the concept that we had, but based on the UNet. So the UNet looks like this. And again, you have the feature map. So the deeper you go, the more concept you have inside the feature map. So again, you have this kind of basic information in the first layer, and the deeper you go, the more you get like image, like concepts of the image. Again, you have this convolution operation and activation function. That's just like this part here that is happening. The max pooling is happening here. So basically, you reduce the information. Again, the idea is to conceptualize the information rather than simply learning, if you want, by heart some part of the image. And so the structure of the UNet is like this. So this basically that's why it's called a UNet. So it's looking like a U. You have the deeper you go, if you want, and I try to explain this by saying that this is the what of the image, and the skip connection that's somehow the where. So So the really impressive thing about the unit is that you don't only learn about the watts inside going down and back up, but you use the skip connection. So here what you basically do is just simply copy this information that was here on the other side. And this permits the network to actually not only know what is around, but also where. So that's what happens in this skip connection. So again, if you want to summarize, like the basic concept behind the unit is that this structure here permits to understand the what of the image, and this is going to be the where. So let's say the what, for example, is going to be the tumor, and the skip connection is going to remind the network of the info. Now we're gonna models, and those are from people that doesn't exist. It's actually a relatively old paper. Now you can even do, I'm sure, much better image than this, but all these people doesn't exist. They were generated by a model. And so you might maybe wonder, like, why generating new data in neuroradiology? Why is this of any importance? And there's some reason. One is that you might need more data. The medical imaging database are relatively sparse or small. There are some diseases that are really rare, so maybe you want to generate data for this to train models, and you might learn something about the data. So there is a paper that I did a few years ago where I generated a lot of synthetic stroke in order to train a model, and I wanted to see if you can improve the performance of the model by doing this. And so I simply took normal images and stroke image, and I just extracted the stroke and added to the synthetic to the normal image, and then I did it carefully so that it works, so that it looks reasonable, and it doesn't look too bad here. And so I generated a lot of them, and I tried to see if I could improve the performance of the training. And so the DICE score is basically, it's like a metric of how good the network works. And here you have the loss function. So that's that you train by epochs, and the more epochs you add, the better the training should be, and the more the smaller the loss function should be. And so this is the DICE score for that was trained on already like a relatively large data set, almost 400 cases, and tested on 74. And when I use the synthetic data on top of it, so I generate 40,000 of them. You see a massive improvement of the DICE score, and you see that it really helps to train the network. And just for comparison, like this is a challenge that was made a few years ago, and the best DICE score was 0.55, and we actually severely beat this with this. So we had much more data in comparison to this challenge. So it's unfair comparison, but still you actually see the difference in quality of. So yeah, so basically using synthetic data to train a network is very useful. And I can show you some results. That was the human label of this stroke, and you see here like maybe like very very small strokes that were detected by the network, and this one too, like you see the here also. So you see that it can really help you detecting small strokes, and so that's kind of interesting. Then there are that's basically two main concepts for generative models, the variational autoencoders, or VAE, and GANs, generative adversarial network. And just going to say a few words how to apply them to radiology and why it can be funny. And so the VAE is a really interesting concept. So the idea is that you take an image and you use a network that looks like this, and you basically try to rebuild this image using this kind of model. And so what this model do is you first have an encoder, and you see already like based on the shape. So what you're doing again is the encoder, you reduce the shape of you have many layers, and you reduce the size of the image to something smaller. And you save this in something that you call the latent space and use a decoder to build this back up. And so you're not surprised that, first of all, yeah, the image might be a little bit less good, but what really happens here again is that you reduce the dimension of the information. So you force, if you want to do this correctly, if you want to decode and have an image that looks like a brain, it forces this structure force the network to learn some concept about the image. So maybe it starts to learn that there's ventricles, and it starts to learn like maybe there's a midline, and maybe like the ovoid shape of the brain. And so it has to learn these concepts, else it's not going to be possible to build this. So that's what the VAE does. And why is this interesting? Because you can then remove the first part, and you just use now the latent space, and you just like take any point in this latent space and press on the button, and what's going to happen is it's going to now it has learned some concept about the image. So it's going to be possible to generate a new image just because this network has learned to generate out of the latent space. It has to learn to generate a new image. So that's one way how you can generate a new image basically from nothing. And I show you some examples here. This is all images that were generated from a VAE, like it's called the introspective VAE, but it doesn't really matter. But you see that it doesn't look too bad. If you look carefully, you see that there's some artifacts yet, so it's not perfect, but you see that it actually works pretty well. There's another funny thing that you can do with this, is that if you don't just pass normal brains, but you pass brains with stroke too, and you do the same, you might hope that again, like this structure force the network to learn some concept about this. So maybe it would not be totally impossible that this space learns that there's what is a stroke. So that's an example of unsupervised machine learning. So you actually don't say the network that there's a stroke, but maybe it might learn. If you do like this, maybe it might learn. So maybe, because again, like if it learns to that there might be ventricles in some cases, and maybe in all cases, okay, but in some cases there might be a stroke, in some cases there might not be a stroke, and so it might learn these concepts. And if you look in a little bit more into detail into this latent space, you can do something that is called latent space decomposition. I'm not going to go into details how this works, but you can basically look at this latent space, and you might hope that the latent space is going to learn the stroke. And if it learns the stroke, it might put all the strokes in one place of this latent space. And this is what you see here. All the cases in dark blue is going to have a stroke, and all cases in light blue have no stroke. And you see that the network did concentrate the large stroke in the center of the latent space. You see them here; they're very small, but you see them here, and some of them are not. And so you can really see that the network here learned in an unsupervised way without us telling us anything. It learned to concentrate the strokes in one place, which is kind of funny. It didn't work well so you see here, this is for smaller strokes. It didn't work well. It did concentrate, but a little bit, but less. But for larger stroke, yeah, it worked a little bit more. But again, like you didn't find all of them, but still, it's kind of interesting to see that it learned something without us teaching it anything, basically. And I just showed you that there's I found this paper that did exactly the same. They also use this latent loss and try to separate between the normal image and the lesion, and it seems to work well. They could publish this. Yeah, and the second way you could use generative AI is called GAN, and GAN is a very smart method too. That the idea is that you're going to train a network. So you're going to build something like this. You have the real image. You're going to put them here, and you're going to try to build fake image based on noise. So here you simply are going to have noise, and you try to generate fake image. At the same time, you use a discriminator. So you use a second network that has to task has to discriminate between real and fake. And so you're going to try to build fake image. And at the same time, you're going to have a network that's going to try to differentiate between fake and real. And And the joke of this is you're going to train the networks at the same time. The discriminator has to learn how to discriminate between fake and real, and the generator has to build image that looks as real as possible in order to avoid the discriminator to find the difference. And I can show you like this is how like one training. So here, so the first step is going to be noise, but it's going to learn better and better to generate the image, and the discriminator is going to have more and more difficulties to differentiate them. And again, you can generate image of, this is again diffusion weighted images of the brain that looks very, very realistic. The last thing I would like to say a few words is the foundation model. That's very recent. Like this term was only coined about 2 years ago in this paper. And you know, that's what all ChatGPT and so on are based on, foundation model. And so it's really like the next step in machine learning that occurred and seems to work really well. And here, foundation models are basically trained in an unsupervised way in a very, very large amount of data. And again, it's like the next step. So if you want machine learning before deep learning was really homogenizing learning algorithms. So if you want like logistic regression, so you try to generalize the learning. Like deep learning is the next step, is you try to homogenize the model architecture. So the convolutional neural network, for example. So you try to homogenize the architecture, and the next step, the foundation model tries to homogenize the model itself. So you actually don't even have one model, but it actually learns to learn somehow. And so those models get trained on a very large number of training data, and you can then adapt those models to the different tasks that you want. So you can ask it to answer questions, you can ask them to build images or to recognize objects. It actually adapts to these different tasks, and yeah, that's a very exciting. And yeah, I think we're in the middle of it. So yeah, so to conclude, what is the future of AI application to radiology or to neuroradiology? I like this comparison with autonomous driving to a little bit try to dampen a little bit to reduce a little bit the expectation. Like I think a lot of people get very excited, but on the other side, it's very complicated. And you know, like driving a car, you might need a few hours as a human to learn how to drive a car, but radiology is very complicated. And even after 10 years of training, we all still struggle with some cases. And yeah, and despite this, like despite the you know, so the complexity is much higher in radiology compared to just something like as simple as driving a car. It evolves over time. So radiology is changing over time. The disease are changing. You know, the technique, the methods are changing. And yeah, and the investment worldwide is much larger in you know, like I found some numbers with like autonomous driving, there's like 200 billion spent compared to maybe 2 billion in radiology. So the investment is much lower, and despite these investments, like autonomous driving is still not there. Like, you know, maybe Tesla, they have some autopilot, but it's still not there. And it's very simple. Driving a car is really, really simple, and comparison radiology is so difficult. And so, you know, there's very good reason to believe that it's not going to be that easy to have like a fully automated, you know, machine learning is going to replace us within a few, within the foreseeable future. So yeah, so maybe you know this Gartner hype cycle. I think it's you know, it's really showing the reality of invention, like the technology, the expectation comparison in time, and there's always like a huge peak in expectation when something new is coming out, and then there's like a drop of this disillusionment where yeah, not as people believe, and then there's like a slow slope of enlightenment, and we might now with AI and radiology be in this slope, or even down here. Yeah, the hope that, you know, the expectation have not been fulfilled in the last few years. And I've even found a paper saying calling acceptance crisis and showing like that's the number of job posts with AI. I think that's in the US, but depending on the different fields where you where the job post has been made, and basically in healthcare, like despite that we constantly hear that how AI in healthcare and so on, in the job post it's just above construction, and you actually see that it hasn't translated in the reality of of the world. So yeah, that's it. But I think that the future is going to be having some kind of help from AI to to assess your case, and it might speed up your work and it might improve your work, and I still think that's the way it's going to be. All right, that's an image of the Alps. I think it's a picture I took last year from a plane, and yeah, thank you very much for listening.